运算啊。那大规模运算这个问题呢，其实已经有一阵子了。那在科学界里面算是已经注意这个问题很久了。但那这次是请到中央研究院的李洪春专案经理来跟各位介绍啊。那这是中研院的这个网格计算中心或者网格运算中心，在这上面已经努力了好多年了那在这上面也非常多的成果。那这次请吕经理来跟大家介绍一下有关这网格运算的一些在里面已经 open source 的一些东西那在下面我们是请到那个 Google 的那个 Christophe Bisciglia 来跟大家讲在 Google 这边怎么样去处理或者怎么样去解决对于这个大规模运算的这个问题。Okay. So now now it's English. Okay, English only. So let's welcome first Mr. Hongchen Li from Academia Sinica about the computing and open source.
Okay, good afternoon, everybody. My name is Hong Li. I'm from Academia Sinica, and well, just to say that I'm actually stationing at CERN right now because we are in the past. We are working together with the European Grid project, so I'm being there to join their project for a long time. So today I'm going to give a talk about this grid computing. Before I start, just wondering how many of you have heard about grid before? Could you please just raise your hand? It seems not so many, so okay, I try to explain a little bit what the grid computing is, and then I will talk about some tools that we are using for developing the grid application. And well, this is my first time to face the open source community. So actually, what I do select some examples which are open source. I mean, from my point of view, open source is something is the source code is available and you can modify and distribute it freely. So okay, so let's just start. So today I'm going through these three subjects. The first thing is that simple introduction about what grid is, and just give you some conceptual ideas about what is the grid. And and then I will go through the current status of the grid application development and point out some issues in this topic. And then I will give you some example application that we are working on, and how we deal with this application using the open source tools that we are working right now. So, what's the grid? The first thing I want to emphasize is that grid is the aim of the grid is to provide a computing infrastructure. And actually, this term was invented by these two guys, Carl Castleman and Ian Forster in 1998. So the idea was inspired from the power grid, because nowadays when we are using some electronic devices, we don't need to worry about where the power is from. We just need to plug our devices into the power outlet. You can get the power very easy, and it's you don't need to worry about what's the source of the power, how it's generated, and you just use it. So the idea of the grid, the computational grid, is to also trying to implement this idea so that in the future, people just need to connect your computers into the network, and then you get the computing power very easily, and it's cheap. So this is basically the idea of this, the original idea of this grid computing. And by that time, they also initiated a project which is now very famous project about green middleware. It's called Global's project. So after 2 years of the development of the implementation of this idea, finally they wrote a paper which is called An Autonomy of the Grid. So in this paper they also point out a concept which is called virtual organization. And this is because in the future in the grid, because the users are coming from different use case, different application domains, and the resource provider is also could be heterogeneous, could be has different policies of managing their resources. It could be a computing center, it could be a desktop like you are just using. So how to efficiently using these resources and how to efficiently to share these resources is based on the concept which is called virtual organization. So what is virtual organization is that a group of people who has a very similar purpose in their, for example, in their working, or for example, their objective. For example, like you are the open source community, you can form a virtual organization and then share the resources among all of these people. And so this is basically the idea of this virtual organization. And because grid is a global system, in other words, it should be an open, and it should be providing some high-level services. For example, if you can do something in your computer, you will never need to use the grid. Okay, so here at grid, we are going to talk about this something that you cannot do with a simple computer or a small class of computers. So here is some definition of the grid system. It's coordinating resources that are not subject to a central control. So it's distributed and it's controlled by different rules, different policies, and different administrators or the owners. And so to connect all these things together, you need the open and general purpose protocols to interface all these heterogeneous computing resources. And as I said before, it should provide the non-trivial quality of the services. So in summary, what is the grid? Grid is about the resource sharing, and nowadays we know that when you are doing the computing, you are touching with the computation and the access of the data. So basically you have to access the computing power, and to access the data which are maybe widely distributed on the internet. So if you make an analog, the World Wide Web is about the share of information, so the World Wide Grid is about the sharing of the computing power. So this is a very simple idea of the grid. So in overall, the dream is to build up a global computer. Actually, this idea is not a new idea. 20 or something 10 years ago, there is also an idea to build up global computer. But actually nowadays we have existing infrastructures that allowed us to simply build on top of it to implement this idea very easily. For example, now we are all connected with the internet, and we have very high-end computers. So this is a picture showing the dream. So for example, you are here using a very simple laptop. So when you click some button, you send out your process to somewhere in the world, maybe a data center or cluster or other people's computer, and there your job is processed. And during the processing, maybe you get the data from the other side of the world, and then you produce the data and put it on the other side of the world. So in the end, this is the dream of the global computer, and this is so-called the grid. So this is just a concept. So to implement this, you have different kinds of means. But later I will describe about this development and what kind of software layers you can have in order to achieve this dream. But what I say later is not just one solution. So maybe in the open source community, there are some better ideas, some good ideas which can achieve this dream easily or efficiently. This could be part of the grid computing. So let's have a look at the real world case, the reality of implementing this grid infrastructure. So what I want to emphasize here is that building a grid is not developing a computer or building up the network. It's purely a software development. So the idea of the grid is to build on top of the existing computing infrastructures, and we call this a computing fabric. And we based on the internet and also the distributed computing centers and maybe your desktop, for example. And because we are not talking about something like word processing, something like a simple hello world application. We are talking about some scientific challenges which needs scientists and also the scientific communities needs to put the effort together to realize some, to solve out some scientific difficulties. So in our case here, I will give some introduction and give you some simple description about these two scientific challenges nowadays. For example, the high energy physics, which is the most important driven force of this grid development. And the other application is, which is more related to our life, is so-called biomedical applications. And there are also other important applications coming up, because nowadays we have grid softwares becoming mature right now. So here is just an example of the European grid project. So we show it on the Google Earth. So the marks on it is actually, they are the clusters or the computing centers, which are contribute the resources into these grid projects. So they are connected with the high performance network, and they can share the resource with each other. So on the other side, you have the application domain users. Different users has different application requirements. So how to link this part together is using something I call this grid software. So what the grid development is actually to build on top of this infrastructure, a software layer which can allow the users to, or the application users to easily access those infrastructures in a simple way. So what kind of driven force we are talking about is a scientific challenge. So here I give you the first challenge from the high energy physics. The idea, the challenge here is to find out this. I'm not really a high energy physics expert, so maybe I say something wrong, our chair can correct me. So basically, this is the idea to find out a particle, a very small particle, which is called Higgs particle. And this has something related to the question about where the mass is from. So in order to do this, we have to build up a very large physics instrument, which is called accelerator. And this is the biggest machine in the world, which you have the particles collide each other in a big ring. Actually, the ring is about 27 kilometers long, and the particles collide with each other in a speed of about the light speed. And then it produces a huge amount of data per second. So for example, here we produced around petabyte data per second. And of course, there are some detectors on it which to detect all these events which generate by these collisions. And then this data will be processed online, which means on the hardware, to build out the data into this rate about 200 to 1500 megabytes per second. And then it goes to the computer. So this is the first tier. These machines was built on top at CERN. So the first data coming out, it goes to the tier 0 center, which the CERN computing center, which we call it tier 0 in this architecture. And then, because this data has to be preserved and then to be reprocessed and to be redistributed in order to back up the data or to share the data among these physics around the world. So in total, we may have thousands of the users around the world who like to use this data to analyze them, to find out the Higgs particle and then to get the Nobel Prize. And so there is a process which is called central production, which is the aim to achieve the throughput rate to distribute all this data to all the tier 1 centers in this row. So as you can see, Taiwan is one of the 12 tier 1 centers, data centers in the world. So Taiwan is also a very important role in this project. And then there are the second tier, which is a local data center, and then there's institutes where the users can come back to access this data for further analysis. So you can see here it requires a lot of disk space or storage spaces and the computing powers to deal with this problem, and this cannot be offered by a single data center. So the idea is to use the grid to distribute all this data and to reprocess this data. So the requirement of this application is that we have the very fast production rate. So in total, we will reach about 10 petabytes per year. And this, because the accelerator is operating in a 24/7 order. So you have to be online for this operation. So you can, as you can see, there are a lot of management issues and application issues in this kind of application. And also the user has to have, we also need to provide the user a very easy interface to access this system. Okay, so the other application is what I'm working on is so-called drug discovery. So just to introduce the first step of the drug discovery, it's called high throughput screening. So basically, the biologist has a very large set of the compounds, which could be some potential drugs inside for some specific disease. So what they need to do is to take all this data, and then they take another, the target virus, and they put into some high throughput machine, and to see if there are some binding affinities or binding efficiencies between those compounds and the disease target. And basically, this process is time and money consuming, because as I say here, it requires you to take about $2 for each this screening. So if you have, for example, millions of these compounds, you can imagine how much you have to pay. But then thanks to the computer-based modeling, you can use computer to simulate this. And this also saves you quite a lot of time, because normally you want to identify virus, you need a long wet lab process to get the real virus protein. So you can use DNA sequence, and then you can simply do the modeling using the computer. But again, if you have quite a lot of these simulations to do, you need a lot of time to do it if you work these things on a single computer. So basically, I give you an example here. In this case, if we go through the 300,000 compounds with 8 targets, it requires you about 137 CPU years if you run this, which means if you have a single computer to run this process continuously, you need to run this for over 100 years. So it's nearly impossible for emergency disease, and this is something that grid can help, because once you have, for example, 2,000 CPUs, you can reduce the duration to 6 weeks. And then you can immediately provide a lot of information for biologists, and they can identify the potential drugs and then directly put into the lab to do some further process to make a real drug. So in this use case, we have the grid provides you on-demand resources, and what the users can achieve, can benefit is to reduce the cost, and sometimes for emergency disease, this is something very useful. So this is some exercise we did last summer. We tried to identify the potential drugs for the avian flu last year, and so as you can see, we don't have so many resources in Taiwan, so we joined the force with the European Grid Project and some biologists from the Genomic Research Center. We just mobilized about over 2,000 CPUs during 6 weeks, and to achieve the selection from 300,000 compounds to about 100 potential hits. And this data is already in the wet lab for further tests. So here is a pie chart about how many resources from different countries, different regions are joined in this project. Okay, so now let's go back to, now I just finished the example applications that the grid nowadays is trying to help. So let's go back to the grid software stack. So in this stack, in the bottom, you have, like my previous slides, you have the resources here, and they are heterogeneous, and maybe because they are not in the central console, so sometimes they upgrade their system, so their technology is evolving. And then you have the users on the top. They are different domain experts. They are not IT engineers. So how to link these two layers together is to go through this layered architecture in the grid software. So at the bottom you have the global software, which we call it grid middleware, and it's basically to define the protocols between the resource sharing and binding. And then on top of it, you have to provide some high-level services, for example, to monitor the user's job, to make accounting, and of how the users is using these resources. And you have the brokering to schedule users' jobs to write the resources so that we can have a more efficient resource usage. And then on top of this is actually our focus today is to talk about the application layer, and actually there is something extra between the application and the high-level services, which is the grid application utilities. Because for the application users, they are not IT engineers, so we have to provide something which is easy to use and hide all the complexities to access all these resources or to use all these high-level services. So in this layer, we are focusing on the usability, reliability, and the interoperability, because as you can see here, I give you some example. There are G-Lite, ARC, and something else. So there are also different middlewares to serve these services. So interoperability is another issue for the applications. And then on top of it, you start building your application. So what's the issues of the application development? So the first is that grid application is a large-scale application. So it's not just use hundreds of CPU, but it's using thousands of CPUs and maybe 10,000s of CPUs in the future. And we are trying to address the issue that nowadays we are not easy to solve or even impossible to solve by using a single computer. And grid is dynamic because I mentioned it's not a central control system, so anything can happen. So we have to live with the failures from the resource side. And because grid has to provide some service which can be used by different applications, so it should be generic, and actually it's generic nowadays. So it's not really well customized for a specific application. So this is because, and then you think about different applications has different requirements. So you have to have something to help the application to customize it for the usage. And finally, grid nowadays is still complex. So I would say it's not easy to understand for a normal user. But I mean, for people here, I think it's not a big deal. Okay, so therefore we need something which is called application utilities. So it's something high level, and it's needed for building the grid application. It's still generic, but it should be easily customized to meet different application requirements. If you look into different application requirements, you still can figure out that there are something in common. So you can somehow pick them out and put into this application utility level. And it should be easy to use, should be reliable, and it should be scalable. Otherwise, we are not talking about using the grid. And it should be extensible. Actually, this is something which is the first item. So, I mean, from my point of view, this kind of utility should be in the plugin approach. So here I just give you some examples in the following slides, talking about my current development, the projects I currently involved in the development. So just some examples. So the first two I would like to introduce is so-called Ganga. Okay, here is the website. You can, if you have more interest, you can look into it. And the logo we just invented. And actually the motivation of Ganga is to, it's the following. So running an application on the multiple computing backend, this is the case the user has to face when he tries to, or when the scientist tries to run his applications on a distributed environment. So here you can see a lot of things. Maybe you don't know one of them. But basically you have the grid environment, and you have, for example, local PC, and also some batch systems like PBS, Condor, Sangri engine, whatever there. But those are doing similar things, which are just scheduling your application jobs and to the distributed resources. So when the user comes, he must do many interfaces. It's the situation right now. So, and then it depends on who is sitting back end to serve you for running your application. And then they have to ask, okay, how to configure my applications on different backends. And then at the end, you will ask, can the user get a consistent view of their jobs? Well, it's actually possible, because if you use the modularized approach, it's not difficult. So the idea of Ganga is to allow you to configure once and run anywhere. And how to achieve this is to define some sort of job object which provides you a layer, a plugin architecture. So for example, in the Ganga framework, we provide something about what to run, where to run, and where is your data, and something like that. And all these plugins can be easily extended for different applications. And then it provides multiple user interface for the users. So some users prefer to use command line shell, and someone likes to use GUI or the scripting. That's all possible. And everything in the previous slide can be modularized and plugged into the Ganga framework. And so the user gets a consistent view of running different applications on different resources. And there is also a monitoring and bookkeeping mechanism in the backend. So you don't need to worry about how to get the information of your jobs running in the remote system. And what is very important here is that this is declared as a GPL license. So many people can access the source code and modify it. And actually there are many people doing that this way. So this is just to show the possible interfaces for the user. And what I want to emphasize here for this tool is that because now your application is running on the remote systems, so there are many things you have to monitor. For example, you want to do debugging, and you want to know the progress of your application and your job. So in the Ganga, we actually wrap your application into a job. So there's a wrapper, and then externally there is a monitoring loop which allows you to plug into different monitoring services. So for example, those are the services also open source. So for example, for Mona Lisa, you can send your monitoring information to that server, and then the user can get the relevant information that he wants to see. And the other thing is that job inspection function, which you can immediately see what's produced on the CPU, on the remote CPU, and then if there is something wrong, you can immediately fix your application and then test it again on the system. So everything is modular approach. Then because it's easy to use and it's very easily adopted by different applications because of the modular approach, nowadays we have those scientific applications using it. What's interesting is this ITU community using the same tools to identify the communication channels between different countries in Europe. Using this tool to do this analysis on the grid. And this is the monitoring information. So we try to understand who is using the system and what kind of the application is used through this system. So we can use the Mona Lisa and to monitor how many people in different virtual organizations using this tool. So it's quite amazing because this is we start this monitoring from the beginning of this year, and after 1 year we managed to achieve today actually more than 1,000 identical users. I know this is because this is not a small tool, so it's not compatible with the open source tools that people are developing. So, I mean, these are all the scientists using this tool. Okay, the other example is actually a prototype, which is called Dangan. And again, it's open source, so you can find more information, even the source code over there. And the purpose of this application, of this utility, is trying to establish something, some extra layer on top of your grid systems, so that the application can take the control of all these resources which are allocated from the grid. And then this is something that we can help the application to speed up to shorten the scheduling overhead, which is now a very it's another issue of running your application on the grid. And then you can you can achieve the efficient computing resource usage. And it also provides some failure recovery, and this is a use case of Feng. So I just try to skip all these details about this utility, and this is how it works. So it's submit the grid jobs to the grid resource broker, and then allocate the resource in the world, and then it forms an extra layer by coordinating all these resources, and then you have a central process to communicate with these resources. So by this, you can implement some fancy stuff using these extra communications between you and the resources. So this is something we used for the second event through exercise. So in total, we managed to mobile over 5,000 CPUs in the world to do the simulation. So again, I would say that because we have to live with the failures which can happen anytime on the grid, so failover is very essential for the reliability of the application. So this is the real case that you will see. So well, the y-axis is actually the number of CPUs you are using. So the red dot there is the time you get the resource response to you, which means the time you can start using this remote CPU to process for your application. So as you can see, there is a latency of this of getting this resource available. And sometimes, and then each block is a process of your task. So you can see some workers just stop at some point before the whole thing is finished. That means there are some network errors, something like that. But by using the prototype Diane, we can hide all these complexities and failures, and then achieve a very stable throughput for the users. And actually, this is 100% the success rate of this large-scale application. Okay, the last thing I would like to mention is the AMGA. And actually, because I don't have too much time, so I just say this is something that you can, if you have interest in the metadata, this is something allows you to do the metadata service on the grid. So it provides you some concept to map the metadata architecture and the relational database architecture. So it's, and then the advantage is that you can do the query like SQL language, and you can also do the file system like operations to search for your attribute. And again, it provides a common and abstraction layer on top of different RDB backend, and it provides some TCP streaming technologies, so you can reduce the time of query the server, query the database, and it's then this kind of improvement can also increase the scalability of accessing the database. Okay, and there are also some security controls on the role of each data, and there are different authentication methods which are applied in this system. And what's interesting is that sometimes, because grid is a large-scale thing, so you have sometimes to do the replication to keep your data preserved, and sometimes you have some failures in one side, you can recover all the things from the other side. So it also provides you the different models of the replication of the metadata. So I don't want to go detail of this. And now this is a use case again for the drug analysis. So the question is that the user wants to get the interactive, because interactive analysis of their data, even the process is still ongoing. Because as you know, this application is a large scale, so it takes quite a long time on the grid before you get the results. But using some kind of metadata catalog, you can put some essential information into the AMGA server, and then when some data which is produced, the user can very easily query the AMGA data, query the metadata, and get the result back to show something like this. And so that they can do this complete your simulation analysis cycle at your runtime. within this system. So in conclusion, GREE is about the computing resources sharing. And again, I want to emphasize that GREE development is a software engineering. So it's working on the existing computing infrastructure and is driven by applications. And there are some high-level utilities are needed in order to fill up the gap or the gaps between the applications and the middlewares. And I think this is something the open source community could contribute. So in my opinion, GREE nowadays is just like a punch card age of the computer development. So it works, but it's not easy to use for the users. And unfortunately, this is a work about software engineering rather than hardware invention. So everybody has a good idea, can contribute to build up something that can make this system easy to use for the wide community. And I know there are plenty of good ideas from the open source community, and I hope these examples can inspire you to contribute your work in this world. And because we are also hiring people, so if you have interest, you can contact me to join us to contribute your ideas. So that's all my talk. Thank you very much.
Questions?
We know the parallel programming is so hard, and you introduce this framework. Can this framework solve the parallel programming hard problem?
Okay. For the parallel computing, I think currently this is not something which is very, very important on the grid. Because if you look into all these parallel applications nowadays that people are using, they are, well, more or less they are using about 255 CPUs. This is not a big scale. So this can be achieved in a single cluster or a single data center. So this is not something that we are very, very interested in this topic, but this is very important. Okay. So nowadays, what the GREE is providing is that you have something that you can ask the broker to say that, okay, I want something to support the parallel computing and more than, for example, 100 CPUs in a single site or a single data center. And then the broker can simply deliver your application to that cluster and run the parallel applications inside the cluster. And inside the same cluster, it's just like a normal parallel computing that you are already working. But I mean, this is something very important. Maybe in the future, if we have some new algorithms needs thousands of CPU to do this parallel computing. But now we are focusing on this distributed computing, which requires maybe 10,000 of CPUs at the same time.
Okay. So our next speaker is Christophe Bisciglia from Google, who is the key man behind the university program that has been talked about on the press or the newspapers, that Google and IBM is working together to have an academic data center and work with universities to promote a new way of doing distributed computing or cluster computing. So I'm very happy to have the chance to invite Christophe to talk here. Okay, so okay, let's welcome him.
Okay, thank you everyone for having me here. Second here. Thanks. All right, so as Feng mentioned, I lead an initiative at Google to work with universities and other academic institutions to start changing the way that they think about and teach computation. Really, I'm attacking this directly at the undergraduate level. I make a claim sort of with a lot of these talks that parallel computing and large-scale computing is no longer a novelty topic. It's no longer something that should be limited to graduate students. It's something that we need to start thinking about much sooner. And one of the largest limitations to this is access to serious, large-scale, cluster-based resources. So let me what I'm going to talk about today, I'm going to start out with a little bit of a narrative about sort of why cluster computing is happening. Like, what are the trends that are going into this, which are requiring us to start thinking about this at all levels. I'm going to talk about some opportunities that this creates for free and open source software. With this sort of new way of thinking about computation, it really displaces a lot of the sort of current status quo way of doing things. I'm going to talk about sort of some of the tools that are used in this. I'm going to talk about some of the computational models that we've developed at Google and sort of some of the open source projects that have come up around these. The way we think about computing at Google is probably 5 to 10 years ahead of what much of the industry is dealing with. Part of this is just due to our scale. Part of, I often say that we are on the bleeding edge of high performance computing. So part of my motivation, a lot of my motivation, is sort of preparing academia and really the programming community at large to deal with this before or as it sort of starts to make its debut in the mainstream. A lot of the stuff I'm going to talk about is sort of just bits and pieces that I've put together into this academic cluster computing program. So after I go through sort of some of the software and programming models, I'm going to explain a little bit about how this has all been put together into this program. At the very end, I'm going to sort of just talk about some of the other fun stuff that we do on the open source team, not directly related to this talk or to this program. And then I'm going to leave, hopefully, plenty of time for questions. And also, my talks tend to be sort of very informal and conversational, so if you have a question at any point, don't hesitate to raise your hand. I like to tailor my talks to what you find interesting because, I can talk about, any of this, and I don't want to just listen to myself talk. I'd really like to kind of tailor this to what you guys find most interesting. Okay, so why clusters? Why is this happening? An analogy that I use very commonly when talking about this, and forgive me if this is a little bit too non-technical, but I frequently explain that human beings really only fundamentally understand 3 non-zero numbers, 1, 2, and many. And this understanding of numbers is something we've seen play itself out in the computation industry. When we first started dealing with computers, let's say 50 years ago or so, we had these large mainframes. And all of the users that would share this resource all use the same computer. And this worked for a while. Until you had too many users that you could fit in one room, or you had too many users spread out over a location that you just couldn't all get together. So you saw the development of the client-server model. And so I say, and then there were 2. You had one role for the client and one for the server. And this took us for a long way. What we're seeing now, though, with the internet brings this explosion of users and content. There are so many users out there now, and there is so much information out there now that no single computer can service the needs of all of these people. So what we're seeing now is the need for software to be designed sort of at the server level to be able to scale out horizontally. So as you get more users and more data, we need to be able to deal with that by just adding more and more computers. So you need to think about software and think about servers in a way that when you design this software, that it functions the same whether it's 3 computers or 3,000 computers. So that's what I sort of like to explain at a very high level. Let's think about some of the trends that are causing this here. Moore's Law is something that I'm sure you've all heard of, you're all aware of. A lot of people interpret Moore's law. What it specifically says is that every 18 months or 24 months, depending on who you talk to, the number of transistors that you can fit on a silicon wafer will roughly double. What this has meant for a very long time is processors get twice as fast, every 18 months or so. I remember first computer I had, I think, was a 25 megahertz computer, and then they got faster and faster and faster. But what you may have noticed is within the last couple of years, it sort of stopped. We've sort of topped out in the 3 gigahertz range, and they're not getting faster. What we are seeing, though, is now 2 cores, 4 cores, 8 cores. We've seen demonstrations of processors with upwards of 100 cores. And so like, this is great. I mean, Moore's law does still apply. It's just not yielding the same type of performance improvements that it used to. So when you used to design software and, okay, well, it's not quite fast enough, you could wait, 4 years, and then things are going to be 4 to 8 times as fast, and it'll work. But that doesn't happen anymore. So in addition to that, networks now are getting faster and faster and faster. Bandwidth is getting cheaper and cheaper and cheaper. What that means is 2 computers that are connected by a network are turning into something that is closer to a single computer. It's still not the same. Like there's still different computers, and you need to think about that. The last one that I think is really interesting, though, is storage. Human beings are now creating data at a faster rate than hard drives are able to improve their density as well. So the only way to keep up with the amount of data that we're creating is to add more and more and more. Like we can produce these hard drives all day long, but we can't increase the capacity of them fast enough. So we have to add more and more of these. So what you end up with is the way that performance improvements are coming now are all coming in the form of parallelism. All of the sort of, we're scaling out horizontally is a term that I like to use a lot. So what does this mean for IT? What you're starting to see is larger and larger deployments of, we at Google use commodity PCs for everything. I frequently make fun of our hardware, and I say that we come over to Taiwan and Asia, and we buy all of the cheapest, crappiest hardware we can possibly find because it's cheap. And when you deal with the number of computers that Google deals with, failure is a reality. Every day, I mean, just if you look at the mean time to failure on computer hardware, if you have 10,000 or more computers, even if you buy the best hardware, it's going to fail. And once you're dealing with the hardware failing, it's not really any harder to deal with it failing 20 times as frequently, because you have to deal with the fault tolerance in software. So what also is happening now is we're starting to see consolidation of infrastructure. At Google, we find ourselves building larger and larger data center facilities simply because it saves money. It's cost efficient. You're seeing many corporations doing similar things. You're seeing sort of many data center providers consolidating larger and larger facilities simply because it's more efficient to maintain 100 racks of servers in one place than a single rack of servers in 100 places. So you look at these trends that are going into, and that's sort of what's happening here. And the last thing that I like to point out is that computation is becoming a utility. The way you manage your data center doesn't distinguish your business. If you're a startup, and you're doing some interesting Web 2.0 application or some interesting social application, it's not going to give you an advantage over your competitor if you run your data center a little more efficiently. It might save you a couple dollars, but somebody can still do it cheaper. So you might as well pay them to do it. So we at Google are sort of privileged to this at the, as I said, on the bleeding edge of this. It's my claim that more and more programmers and more students, when they graduate, are going to have access to the power of a Google data center when they graduate. So it's time to start thinking about this now. And so what I've been spending sort of my last couple years at Google doing is thinking about how we can get students and programmers and developers thinking about working with very large data sets. One thing that we're finally seeing happening in computer science, which is really interesting, is we're starting to see computer science sort of serve as the heart and the foundation for all forms of science now. Sort of what we just sort of heard talking about in this last talk is that with these biomedical applications and these high energy physics applications, we're turning to computer scientists to solve the computational needs of all types of science. So really we need to sort of start looking at sort of what we can do sort of from a computation perspective to facilitate this. So I want to talk a little bit about what this means for open source. What's really cool about this is a brand new area, a brand new development. There is nobody with a stranglehold on the market. There is no dominant player in cluster computing. There is, one of the nice things about it actually is that Linux actually is actually probably in a better position because it's easier to manage. Like when you've got 10,000 machines, Linux just works better than Windows. Linux just works better than pretty much anything else out there. And there are very powerful free and open source software solutions already in place. Sort of two big things that go with this are virtualization and large-scale computation. And Zen is a very popular virtualization platform. It works pretty well for Linux because it uses something called para-virtualization, which is if you make your guest operating system aware of the fact that it's a virtual machine, it's much easier to virtualize it. You can do this with Linux because you can modify the source code. You can just tweak it. You can't trick Windows into thinking that it's a virtual machine because you can't access the source code. It's not even a complicated change. It's a small number of lines, but if you can't see the source, you can't do anything about it. And then the other sort of aspect is large-scale computation, which I'm going to talk about a little bit. And this is really all centered around the Apache Hadoop project. And what that is Google has published academic papers about a lot of the developments that we've made that allow us to work with petabytes and petabytes of data. As a result of the publication of these papers, the Hadoop project has spun up and provided an extremely compelling implementation of this computing technology. And sort of the last sort of thing that I'm going to sort of plead to the community here is one of the big areas for development on this is open source data center management technology. It's one of the hardest things because you sort of need a data center to develop this sort of software. I don't have a good answer for this yet. So this is sort of just something I'm throwing out there. We need tools, like in this academic data center that I'm going to talk about a little bit, the one piece of software that we rely on that is not open source is IBM's Tivoli systems management software. Simply because IBM is one of the few companies that has sort of the experience and the access to resources to develop such software. I would love it if there were an open source alternative to it, but there isn't yet. But that said, everything else is open source. Everything that a student would interact with on this academic data center is open source. All it handles is the provisioning of, it handles the, a computer turns itself on, it doesn't have an operating system on it, Tivoli handles provisioning that and then setting up a virtualization layer and then procuring virtual clusters on top of that. So yeah, this is sort of the landscape that we're going into this with. What I'm actually going to talk about today is the MapReduce programming model. It's a way to think about computation and to abstract your problem. If you can fit your problem into this programming model, you don't have to think about concurrency, synchronization, you don't have to think about machines failing, you don't have to think about anything except the algorithm and the science that you're trying to solve here. Sort of something that goes right along with this is GFS, which is the Google file system. It's a very large-scale distributed file system that allows you to store data all across your cluster. You break up your files into little itty-bitty pieces, or 64 megabyte pieces, but when you're dealing with files on Google scale, that's really small, and spread it out. And then Hadoop is the open source implementation of these. So one thing I should be sort of really clear about is I talk about MapReduce and GFS, and these are technologies sort of developed by Google, and then Hadoop is the open source implementation of that. Google has not open sourced the code for these because I'm sure a lot of you have worked in software engineering organizations. There are dependencies that get really, really ugly. If we wanted to open source our version of MapReduce and GFS, we have to open source our entire code base, and It just isn't practical. So that said, the way we've dealt with this is we've provided an academic explanation of how we've built this system and given the community sort of all of the tools that they need to create an implementation. And then with this academic data center now, we've taken it one step further and provided a large platform to create new users, create new developers, to facilitate research and improving these tools and the like. So there also are a couple other interesting technologies that I'm not going to talk about today, simply for time reasons, which are Bigtable and Chubby. Bigtable, so the Google file system is really good at writing data one time and then reading it in a streaming fashion over and over again. So when you're a search engine and you're crawling the entire web and then indexing it and doing that sort of pipeline work, it works extremely well. But if you want to sort of access that data randomly, it doesn't quite work as well. So what Bigtable is a layer on top of GFS that provides random access to data. And there is a developing implementation of Bigtable as part of the Hadoop project. It's not as mature as MapReduce or GFS, but it is getting there, and it's really exciting. The other one is Chubby, which is sort of a distributed locking system. So when you have a large cluster of machines and you're running lots of software and lots of code on it, you need to be able to lock resources, across that. You need to make sure that when you're doing something, somebody else isn't. And Chubby provides a distributed framework to do that in. Okay, so MapReduce. I'm going to try and sort of explain this model here. This is a little bit of a messy graph here. But what MapReduce says is a functional model that you break your computation into two functions, basically. There's a map function. And what a map function does is it reads in some chunk of data. I'll frequently use examples that are focused on search because I work for a search company. But there's nothing unique about this. This works in all problem domains. MapReduce has been applied in many other areas as well. So let's pretend, let's imagine that this is the web, basically. And we've taken the entire web and we've broken it up into many, many little pieces. And then what you do is you write some map code. And what map does is it takes in your input data and it generates a set of intermediate key value pairs. Just key value, key value, key value. You can emit an arbitrary number of key value pairs. And then you can spread this out. If you just write it in terms of here's a piece of input, here are my intermediate key value pairs, no one piece of the computation is dependent upon really what anybody else sees. As long as you know that all of the data will eventually be mapped, you're okay. So you end up with a whole bunch of key value pairs, and then there's this barrier here. We need to wait for all of the maps to finish. And then once all of the key value pairs are generated, we sort of aggregate all of the values for a given key. So what happens now is in the reduce phase, here we've got three keys. You have key one and then all of the intermediate values for it. I'm going to do an example in a minute, which will hopefully make this make a little bit more sense. But what happens is for each key, you have maybe an arbitrary number of values. You get to process now all of those values together. And you get to see, okay, so every one of these distributed map workers that emitted a value for key 2, I now get to see all of the values for key 2 together. But you don't get to see anything about key 1 or key 3. And it's because you have to write your program now in a way that doesn't care. And this is most efficient for processing extremely large data sets when you're I/O bound. This isn't something that we use in real-time systems. This isn't something that we use to process queries. This is when I have a whole lot of data. How do I do something interesting with it? So let me sort of go through an example now, which hopefully will make this make a little bit more sense. And while this is a trivial example, I'll also maybe go over another one as well, but this is the one I have code on the board for. Say you wanted to count all of the words, know how many times every word appeared on the web. Maybe not horribly interesting, maybe interesting, I don't know, but this will hopefully give you an idea of how the programming model works. So in your map phase, you read in all the documents. And then for each word in the document, you emit an intermediate value where the key is the word and the value is 1. This means I saw this word. And then you have everyone do this in parallel, over all the entire repository. And then in the reduce phase, you get basically a bunch of instances of that word and the number 1. So you take in the output key, which is the word, and the iterator, which is essentially going to be a list of ones, and then you're going to just sum them up. And then you're going to emit now your final value, which will be a mapping of that word to the number of times you saw it. So another sort of frequent thing that we could do with this is indexing. If you wanted to map each word to all of the documents that it occurred in. So let's look through this again and pretend that's what I was doing now. The first part's almost the same. So we would go through and we would look at for each word in the document, instead of emitting the number 1, we could emit the input key, which was the document name or the URL or the document ID or whatever makes sense. So now you end up with emitting keys that are the word and a document ID. All right, so now when you go through in your reduce phase and you're trying to generate the pieces of the index, you emit that word and then you emit a list of all the documents that it occurs in. And that's essentially what an index is. And then what you do, sort of when we serve this up now, we would break this up, into, you put a little bit of the index on each machine, you load all of that into memory, and then when a query comes in, you send it out to all of the different servers that store a piece of the index. They all respond, and then you merge sort of the responses together, and you return the best set of results to the user. Any questions about MapReduce before I go on? Because I don't want to keep talking if people have no idea what I'm talking about. Okay, do you want a sort of another example? Okay, let me think here. Okay, let's pretend. So how many of you are familiar with what ray tracing is? It's a graphics application. Anyone? Who knows what ray tracing is? Okay, so I won't use that one. All right, what about this? What about rendering? How many of you guys have some idea of how you render like a 3D movie? All right, so let's pretend we're trying to render a 3D movie now. What you would have and what you essentially end up with is you end up with a model, basically. For each frame in the movie, you have a model, which sort of represents the different objects in that frame. And then you have, that model includes things like the actors and the light sources and things like that. And then what you essentially just have to do is you have to go and just do a bunch of computation to compute what that frame would look like. So what you would do is in your input would essentially be all of the, the timestamps, basically, all the different frames that you would want to do it, and then the model, sort of the position of the model. God, this is going to sound silly because this is sort of a trivial. So this is one of the things I joke around a lot with MapReduce is that it's a really big hammer, and when you have a really big hammer, sort of everything is a nail. This would actually all happen in the map. You would essentially break up your scene into a whole bunch of different chunks, and in the map, your sort of key would sort of be your time, basically, in the movie. And then what you would do is you would get the model. I'm not going to use this example. It's a horrible example. This is sort of one of those places where you use MapReduce to do something trivial. You just sort of use it to break the computation. In each map phase, you would just compute the scene right there, and the key that what you emitted here would essentially be an image for that time in the movie. And in the reduce phase, you would basically sort them. You would make sure, because in your map, you don't always know, it doesn't have to be sequential. And so in the reduce, you would basically just end up sorting. Anyway, I'll be around afterwards to sort of answer sort of more questions about this. I'm gonna go on to what the file system is and how these things sort of play together. So GFS is a distributed file system, and what's really cool about GFS is you have a master, but the master of the file system doesn't really do anything except keep meta information. It basically stores a mapping from a name to a chunk ID. And what a chunk ID basically is, it just is an address on one of these chunk servers. So just like MapReduce schedules computation across many, many machines, GFS distributes your storage across many, many machines. And what's really cool is when you use the two systems together, you can ensure that your data, that your computation is being scheduled on the same physical nodes that store your data. So there's actually nothing going across the network except what you emit as those intermediate key value pairs. So what's also really cool about this system is the master essentially, when a client tries to read something off of the file system, what the master basically, so the client says, I want to read this file. Where is it? It basically gives the client the information it needs to talk directly to the chunk servers. Most of the master is really not involved except giving you enough information to the client to access these nodes directly. This becomes important because you can't run everything through the master. Like, it's a single point of failure in the system. So in Hadoop, you have a single master. At Google, we've actually developed systems that use sort of shadow masters for reading to make reads more efficient. But Hadoop isn't quite that far along yet. So what you end up with is sort of data sort of just broken up into pieces, spread across all of these clusters. And when you have a cluster of, I don't know, say 5,000 machines, and say each machine's got a terabyte of hard disk space, it's 5 petabytes of data. You can't really back that up. Like what are you going to do? Have another cluster right next door that you're going to back that up onto? So what GFS does is it replicates data. So for every chunk of data, we'll put this on probably 3 different machines. Or for some data that needs to be highly accessible, we may put it on 12 different machines. And what this means then is, say data centers are usually broken into racks. You'll have 40 machines in a rack, and you might have 100 racks, and that'll be 4,000 machines. So we'll take a chunk of data, and we'll make sure that we put one chunk on one rack, one chunk on another rack, and one chunk on another rack. Because sometimes bad things happen in data centers, like they catch on fire, or electricity comes through really fast, and there's a big power surge, and the whole rack blows up. So you need to handle the redundancy basically with this replication, because when you're dealing with sort of clusters and data sets this large, there is no practical backup means. So again, this is us handling fault tolerance with software rather than hardware. So this is sort of a summary of these sort of abstract sort of systems that we're dealing with, and these are what's really nice about MapReduce is when you frame your problem in terms of MapReduce, you don't think about concurrency or the cool thing about MapReduce is the model map and reduce are simple enough that non-computer scientists can get it. Normally, it takes about, when we teach a class on this stuff, it's only about a week's worth of teaching material to get students up to the point that they understand MapReduce. So I guess that makes sense that I can't quite explain it in this 45-minute talk. What is really cool though, and I'll bring some links up at the end, is we offered a 5-part video lecture series to the interns at Google, where we taught them the basics behind parallel computing and brought them up to speed with MapReduce and the Google file system over a 5-part lecture series. And these lectures range in time between 30 minutes and 50 minutes. So I'll provide a link to that at the end. So if you're interested in sort of understanding the computer science behind this, there are 5 videos that you can watch that will really sort of bring you up to speed on how to think about problem solving in these terms. So what is Hadoop then? Hadoop, as I mentioned, is the open source implementation of these programming models. They use different names at some point, so let me sort of cover the mapping between what Google calls things and what Hadoop calls things. So instead of MapReduce, they call it Hadoop MapReduce. And instead of the GFS, which stands for Google File System, they call it Hadoop Distributed File System. Functionally, they're the same. HTable is their implementation of Bigtable. Again, very similar. And what's really cool, which was recently contributed to the Hadoop project, was a plugin for Eclipse that IBM made. We really want students to think about cluster computing the same way they think about regular computing. I don't want the kids to think about the fact that there are 1,000 machines, an internet connection away from them. I want them to use their local machine to access these resources. So this plugin for Eclipse allows them to write their code locally in Java, and they give the Eclipse plugin enough information about the server, which is basically the IP address of the head node for the server, for the cluster. And then what it does is it takes their code and it packages it up and it sends it to the server, and then the head node for the computing cluster sort of takes care of the distribution of that code and running that code on all the different machines. And the output of their code and the input of their code actually is already on the cluster. When you're working with web scale data, the student probably actually doesn't have that much storage space locally. The web, when we crawl the web, oh gosh, this was so many years ago, so I can probably say it. A couple years ago when we crawled the web, it was like a terabyte worth of data when it was compressed. Now I'm sure it's much, much bigger. And back then nobody would have had a terabyte of storage space. And when you generate an intermediate data set from a 1 terabyte data set, it'll probably be about a terabyte as well. Like an index for a repository is generally on the order of the same size as that repository. And so you can't actually move that data across the network connection that exists between the developer writing the code and the computing cluster that hosts the data and runs the code. So all the data just stays on the cluster. And you sort of come up with ways to view it. And a lot of times you'll generate statistical summaries of your data and pull that back over so you can see, okay, well, if I really want to find this chunk of information in the data, let me just pull that over rather than pull the entire data set by. So Hadoop is already in use by a lot of people. One of the things that I sort of say about Hadoop, which is really cool, is that open source is usually, it's very, very compelling sort of for number 2 players. For people that sort of, Google really has the lead in sort of a lot of this sort of computation technology. And as I said, for a lot of practical reasons around software engineering, we can't release the code. I don't know, maybe there are competitive reasons as well, but I've been promised that it's software engineering reasons. Anyway, so Yahoo actually employs the core development team for the Hadoop project. And then Facebook is one of the major users and contributors. And many, many small startups are starting to use this now. And what's really cool is they figured out a way to use it with Amazon's Elastic Cloud computing platform. How many of you have heard of EC2? Okay, so let me sort of digress just for a second here. Before, when I was talking about computations becoming a utility, and it's something that doesn't distinguish you from your competitors, Amazon really sort of embraced this a couple years ago when they gave you the ability to rent commodity Linux machines. You can just run a Zen virtual machine on these for about 10 cents an hour. What this means now is if you're a startup and you have a new idea and you want to prototype it, let's go back 5 years, you have to raise a bunch of capital, you have to buy yourself some servers, you got to get someone to maintain those servers. I mean, you're looking at $20,000 in IT costs minimum. And if you're an entrepreneur and you're an innovator, that means you essentially have to sell equity in your idea to cover those costs. And that really sucks because you don't even know if it's going to work yet. With Amazon's platform now, you can just rent the computers you need. Until you figure out if the idea works, figure out how you're going to scale, you basically pay for things as you use it. So let's sort of go back to Hadoop now. They've created templates now which allow you to create Hadoop clusters on Amazon's computing platform. You have a question? No, okay. So what's really cool then is you can sort of experiment with your idea on a small set of data, get your algorithm down. Know that, okay, this works now. And then when you know you've got it right, you can rent 1,000 computers for a day. And then you can run your computation, and then you give the computers back. Wash your hands. I had nothing to do with that. And Amazon is still maintaining their computers, and presumably somebody else the next day is using them. And you, as the developer, have gotten what you need out of the system as well. So I want to be really clear that this is not a Google thing. That this is something that Google has developed. But this model of computation is being adopted by many, many, many other people. It's proven effective for many applications outside of search. Many, many startups are starting to use this because it allows their engineers and their developers to sort of focus on the algorithm rather than the logistics of maintaining a complicated distributed system. You can pay somebody else to do that for you, and you can focus on your code. Okay, so putting this all together into Google's academic data center. So how did this start? How am I doing on time? Okay, perfect. So how did this start? So I've been working for Google for the last 5 years now, and over that time, I've probably interviewed upwards of hundreds of college students, and I started to recognize this very consistent pattern, is that, all right, let's ignore all the kids that slip through the phone screen process and actually weren't smart. Let's take the very, very smartest kids that I've interviewed. I'll ask them to come up with an algorithm to solve a problem, and they'll do a really good job. They'll come up with a really compelling algorithm, and then I'll say, okay, but we're Google, and we have like almost 1 billion users, and we work with more data than I even really know how to think about. What would you do if you had 1,000 times as much data? Just look at me and they start scratching their heads, and like, they don't know, and like I can't really hold this against them because they've had no exposure to this. And so what I end up seeing in interviews is, rather than coming up with solutions to problems, I see the students trying to sort of grasp these fundamental issues of parallelism. And that's really an interaction that you should be having with your professor. I mean, if you can imagine getting your final exam, 10 minutes after being asked to think about an idea for the first time, nobody wins there. Like, I don't win as an interviewer because I don't really know if they got it or not. And they don't win as an interview candidate because, I can just imagine how many of these kids get home and 3 days later or a week later, like, oh, I totally get it now, let me call that guy. Like, no, I'm on to the next, batch of students here. So I started to think about, what we could do with this here. So this started as a single course at the University of Washington. I went back to some of my professors there and I said, hey, I really want to help undergraduates think about large-scale computing. So I went then to my vice president at Google and I said, so I want like $100,000 to go buy some computers and go to school and teach this class. And at first they told me to go away, and then I didn't. And I kept bothering them, and I said, no, I really need to do this because I don't know, it's irking me. And so finally they said yes. And so I brought in a cluster of computers to the University of Washington. It was 80 processors, 160 gigabytes of memory, and 24 terabytes of raw storage space. That was roughly equivalent to all of the computational resources that previously existed inside the department. And this was, and all of the faculty were looking like, why are you giving this all to undergrads? Undergrads kind of get a sham deal in academia. They're sort of like the bastard stepchildren in academia. If it's not like, graduate research or, something for, anyway, so I said, I don't care, I'm gonna go work with these kids because they're my age. I was like, this is a year ago, so they're only like 4 years younger than me at this time. So we offered this course, and the first time we did it, we sort of didn't know what we were doing. So it was me and 2 other engineers, and we tried to pretend we were teachers, and that was pretty humorous at times, because we're not, we're engineers. So after the first course offering, many things were clear. The first being that we aren't teachers. The other thing that was really clear is that the students really liked it, and that there really was a need for it. So the University of Washington got much more closely involved in the second offering of the course and provided teaching resources. And then we sort of worked together to develop a 6-week curriculum, which we released under a Creative Commons license. So lots of other universities have used this since then. Tsinghua University in Beijing used this, Carnegie Mellon has started using this, MIT has started using this, Stanford and Berkeley are both going to be using something based on this next year. And there'll be links to this, well, there are links to this up there. And that is also the link that you can find that 5-part video lecture series at. So if you're sort of curious to kind of understand a little bit more about the programming model, that'll give you, there's, as I said, there's about a total of about 3 hours of lecture material, along with slides and suggested readings and things like that. You can do it in a week. If you just took like 1 lecture a day, did the readings, slept on it, went through it the next day. So we realized, once this sort of started out to be really successful, I went back to tease the vice president who told me no at first. And I said, okay, so this is working out really well, and I want to do more of this. And we started thinking about, like, it really doesn't scale to put a cluster in at every school. It's just, that's going to be really expensive. The schools have to, like, actually the hardest part about this is managing this cluster. Like, the University of Washington support staff is already overworked, and they probably have more resources than many computer science departments. So, if I go to, San Jose State College and like, hey, can you maintain 100 computers? They're going to look at me and be like, no. Like, so we sort of decided we're going to consolidate these resources. The other thing we realized is, okay, well, now that we're talking about using 1,000 computers instead of 40 computers, we don't really have we need a technology partner. So Google has data center management technology, but our customers are engineers, some of the most technically competent people in the world. When we're talking about working with undergraduate computer scientists and sort of university support staff, they probably couldn't use our systems. And honestly, our data center management software is probably one of our big competitive advantages, so we might not want to do that as well. So IBM was very eager to help us because they actually are going to get into this business of providing utility computation services. So this is a great sort of way for us to work together and for Google to sort of bring our expertise in large-scale computing and IBM to sort of bring their expertise in enterprise management and working with customers. I mean, they've worked with people from large banks and telecom companies to small and medium-sized businesses. So together we were actually able to create a surprisingly compelling offering that is, still shaking the bugs out, but we're getting there. So this is now serving as a platform for education and research. So while Google wasn't able to open source our versions of MapReduce and GFS, we were able to sort of create this platform where we do fully support the project. I mean, I'm here talking to you about it. I blog about this publicly from Google. There are people that yell at me like, why are you promoting Yahoo's computational platform? And I'm like, well, because people need it. So, I mean, that is one of the sort of also the sort of nice sort of, side points about Google is there really isn't a lot of these, corporate politics in here. I'm actually able to go and talk to people about the best things, if they're Google or if they're open source or if they're sponsored by one of our competitors. So a lot of development is going to happen with the Hadoop project, and I'm really hoping that this will also create a platform where we can sort of research sort of some other ways to manage these resources. Another thing that's really cool about this is this is going to allow us to give grants in the form of computational resources rather than money. So let's think again about that scenario where pretend you're a professor and you come to Google for a research grant, and we give you $100,000. You might want to go spend $50,000 of that on hardware, so you can do your computation. It'll probably cost you another $25,000 or $30,000 to maintain that hardware and administer it and deal with that. And let's say you're probably going to need a grad student to be involved, so there's another $20,000. You got no money left over. So if we could just provide you access to an extremely large computational resource, one, you save all of your overhead costs, and two, we can actually give you access to a much larger resource for a short period of time. So that's why this is all kind of exciting to me. This is something that, I don't know, many of you might have heard that Google has this notion of 20% time, which is where we try and get all of our engineers to spend 20% of their time doing stuff they're not supposed to, or what's not part of their regular job, which isn't their primary project. And so what happens is when you tell engineers to do whatever you want with some of your time, they come up with ways to think about, so like senior managers and executives are really good at keeping track of the big picture, keeping the boat moving in the right direction. But a lot of times they miss the small stuff. They're a little bit, as the company grows, they become distant from the people that are actually doing the work. So encouraging your engineers to spend sort of time working on other things is a great way to sort of to catch that small stuff, that prevents stuff from slipping through the cracks. So that's sort of the end of what I'm going to talk about with respect to Hadoop and my work at Google. I'm going to, because I do work for the open source team and they paid for me to come out to Taiwan and talk to you guys, I'll go and give some shout outs to some other really cool stuff that we do at Google. So at Google we use a lot of free and open source software. In Google data centers, it's almost all open source stuff. We have over 1,100 free and open source software libraries that we're using in Google Code to provide all the services that you guys are used to. And this isn't even counting, Linux, GNU, GCC, etc. All production servers at Google are based on Linux, which is kind of awesome. Another cool thing we've done is we've open sourced about 100 Google projects, ranging from things like Google Gears, which is a library that allows you to sort of develop Web 2.0 applications that have some offline state. It allows you to sort of keep some, like a local database of some information about the service you're interacting with, so you can use it when you're not online. See, another cool one that we've recently released is a system called Ganeti, which is, it's one step in that sort of data center management. It doesn't scale up to the full data center, but say you have a rack of like 30 or 40 servers using Zen and you want to run virtual machines on top of that, Ganeti will give you an interface to them to sort of treat them like a cluster. You can say, okay, here's a virtual machine, make sure there are always 3 of these up, and it'll sort of take care of that for you. there's code.google.com, and on code.google.com we host over 53,000 open source projects, and we're getting over 10,000 daily commits now. This is probably, this is a lot of code being committed, a lot of code we're keeping track of. And we don't charge anybody anything for this, but it does take a lot of resources and a lot of time. But it's something that we sort of just want to do for the open source community, because they've given so much to Google, like we've built ourselves on free software. So one of the other things we do is Summer of Code. I don't know, how many of you heard of Summer of Code? Okay, I believe there's someone else here talking about it a little bit more, so I'm just going to give these really high-level points here. 900 students in 90 countries at over 400 universities last year. So a lot of people ask sort of how did Summer of Code get started, and Larry Page, one of our eccentric, kind of crazy sometimes founders, went to my boss and said, hey Chris, solve the problem that university students don't write code over the summer. So with all of these students, we pay them, I think, on the order of $4,000 for a summer to work with an open source project. This involves about 1,500 mentors in 130 projects. So what this does is it gets students working on open source sooner. So they spend a summer learning about how do I become a committer? How do I work with a remote development team? There are a lot of sort of software engineering challenges in open source that are just fundamentally different from the type of software engineering challenges you face if you're working on with a local software development team, oftentimes in a proprietary situation. This resulted in 2.5 million lines of code written by students, which is also kind of cool. The last thing isn't really open source, but it's something that our team had a lot to do with, and it's open in the sense that the APIs are open, but we just announced Google Open Social, which is a set of APIs that allows social networks to interact with each other. One of the things that a lot of people think sort of with networks, that the value of the network increases with the square of the number of nodes. I actually contend with social networks that this isn't quite true. For example, like there are so many people on MySpace now, all I get is like MySpace spam, like friend requests and things like that, and it's completely like, and on Facebook now, I just realized the other day I had to go in and lock down my profile so people from work don't see my drunken party pictures, you know? And so I actually want a way to kind of segment my sort of social network a little bit. And what Open Social does, it gives you the ability to write an application that can run on MySpace or run on Orkut or run on basically everyone that matters except Facebook. So we'll see how Facebook reacts to this. It should be interesting. Facebook has their own sort of platform, and Facebook has about 45 million users, and the people that are committed to Open Social now comprise over 200 million users. So we'll see what happens. It should be really interesting. Questions? Hasn't let me off the hook that easy.
Okay, so we have like 2 minutes for questions. Any questions? No?
Okay, so go watch those videos because that'll probably give you all kinds of questions. And there's a forum on Google Code for Educators, which is on code.google.com/edu, where you can sort of ask questions about the technology, about the programming models, about all kinds of stuff. And there are people sort of from Google and people in the community that will sort of help you kind of work your way through and wrap your head around some of these ideas.